Today we will introduce Leegent 3360, a new generation release agent designed for press-formed refractory bricks. This presentation focuses on its interfacial control mechanism, industrial validation, and application performance in magnesia carbon and alumina carbon brick production. The presentation is divided into 8 parts. We will start with the background and the limitations of conventional diesel and engine oil release systems, then move into the molecular design of Leegent 3360, its interfacial behavior, key performance results, cost-benefit analysis, application guidelines, and finally its engineering value. In refractory brick press forming, the release agent may look like a small auxiliary material, but it has a direct impact on production efficiency, mold life, surface quality, workplace safety, and total operating cost. Traditional diesel and engine oil systems are still widely used because they are familiar and easy to obtain. However, they also bring several persistent problems: high safety risk, unstable release performance, limited production efficiency, surface contamination, and hidden long-term cost. Leegent 3360 was developed to address these issues through hyper-branched polymer technology. Its purpose is to form a more uniform, more stable, and lower residue lubricating film on the mold surface, supporting safer, cleaner, and more efficient demolding. In refractory brick production, conventional diesel and engine oil release agents create problems in 3 major areas: safety, efficiency, and cost. First, there are safety concerns. Under hot pressing conditions, diesel and engine oil may volatilize, producing smoke, odor, and potential fire or explosion risks. Second, there are efficiency losses. These oil-based systems are prone to nozzle clogging, non-uniform spraying, and low release capacity per application. As air salt, operators need to respray frequently, which increases downtime and interrupts the production rhythm. Third, there are hidden costs. Although diesel or engine oil may appear inexpensive at the purchase stage, the total cost increases when mold wear, scrap rate, cleaning, labor, maintenance, and production stoppage are included. So the key point is this: conventional solutions are not truly low cost when evaluated across the whole production system. This page shows the causal chain behind conventional release agent failure. The root cause lies in the physical properties of diesel and engine oil: relatively high surface tension, easy volatilization, and a tendency to carbonize or form residue at elevated temperature. These weaknesses lead to poor film coverage, local rupture of the release film, and unstable adhesion at the mold product interface. Once the film becomes discontinuous, the product may stick locally to the mold, causing higher demolding force. Higher demolding force then leads to increased scraping, abrasion, and mold surface damage. As the mold becomes rougher, wetting becomes even more difficult, and sticking becomes more frequent. This forms a negative loop: rougher mold, poorer wetting, higher sticking risk, higher demolding force, and faster mold wear. The core of Leegent 3360 is a hyper-branched hydrocarbon polymer system combined with nano-oxide reinforcement and polar anchoring groups. The hyper-branched polymer structure provides low viscosity, good spreading behavior, and improved film forming ability. Its controlled molecular weight distribution also helps improve consistency from batch to batch. The nano-oxide component works like a micro-reinforcing skeleton inside the release film. It improves film strength, thermal stability, and resistance to rupture under pressure. At the same time, polar functional groups help the film anchor more strongly onto the metallic mold surface. Therefore, Leegent 3360 is not simply an oil layer, it is a descent interfacial film system built from organic film formation, inorganic reinforcement, and interfacial anchoring. For a release agent, the first critical question is whether it can spread quickly and uniform lie on the mold surface. This is usually evaluated by contact angle. A smaller contact angle means better wetting. Better wetting means the liquid can form a more continuous film instead of isolated droplets or dry spots. Leegent 3360 has low surface tension and strong compatibility with the metal surface. Therefore, it can form a very low contact angle on steel molds and approach near complete wetting. By comparison, diesel and engine oil tend to show higher contact angles on rough or used mold surfaces. They are more likely to form local dry areas, uneven oil distribution, and unstable lubricating films. This difference is important because local dry spots often become the starting point of sticking, scratching, and increased demolding force. This page explains where the separation happens during demolding. The ideal situation is a to-be interfacial separation. In this mode, the product separates from the surface of the release film, while most of the film remains on the mold. This allows one spray to support multiple demolding cycles. For conventional diesel and engine oil systems, separation often occurs at the B2C interface. In other words, the release film is easily pulled away from the mold and transferred to the product surface. When this happens, very little effective film remains on the mold, so the operator has to respray frequently. Leegent 3360 improves this behavior through chemical anchoring. The film is more strongly retained on the mold, allowing repeated demolding with less spraying and more stable release performance. From this section we move from mechanism to performance validation. A release agent should not be evaluated only by unit price or by one successful demolding event. It should be evaluated as a complete production tool. This presentation uses 8 performance dimensions: basic physico-chemical parameters, wetting and spreading ability, interfacial anchoring capability, film strength and stability, high temperature stability, and non-coking behavior, sprayability and rough mold compatibility, release efficiency and mold service life. These dimensions together give a more complete view of real industrial performance. This table compares diesel engine oil and Leegent 3360 from the viewpoint of basic physico-chemical properties. Leegent 3360 has a suitable viscosity for spraying and spreading, while maintaining a clear flash point of about 260 degrees Celsius. This supports better operational safety than conventional oil-based systems. Its surface tension is much lower, around 24.3 millinewtons per meter, which helps it spread rapidly across the mold surface. It also shows stronger bonding, energy, and higher film strength, which are important for keeping the film intact during pressing and demolding. In short, the performance advantage does not come from one single parameter. It comes from a combination of lower surface tension, stronger anchoring, better film strength, and improved thermal stability. This page focuses on wetting and coverage under industrial conditions. Because of its low surface tension and polar anchoring effect, Leegent 3360 can achieve almost complete wetting on steel mold surfaces. Even when the mold has micro-scale roughness, the film can penetrate into small surface valleys and form a continuous protective layer. Diesel and engine oil behave differently. They are more likely to remain as local droplets or discontinuous patches, especially on rougher mold surfaces. This increases the risk of sticking. The industrial results show that Leegent 3360 can expand the applicable mold roughness range from the conventional level of RA below 1.6 micrometers to approximately RA below 6.3 micrometers. This means better tolerance for used molds and less dependence on frequent polishing. The on-site images provide a direct comparison with Leegent 3360. Even a relatively rough mold surface with an RA value around 6.3 micrometers can still be covered by a continuous and uniform film. By contrast, diesel or engine oil may already show uneven spreading, local dry areas, and film rupture even at an RA value around 4.5 micrometers. This explains why Leegent 3360 can maintain release stability under more demanding mold surface conditions. This page explains how chemical anchoring improves continuous demolding. Because Leegent 3360 forms stronger interaction with the mold surface, demolding T&Ds to follow the A-tube separation mode. Most of the release film remains on the mold, while only a controlled amount transfers to the product surface. The practical result is a much higher number of demolding cycles per spray. In magnesia carbon brick production, one spray of Leegent 3360 can release about 12 to 15 bricks on average. In alumina carbon brick production, it can release about 4 to 5 bricks per spray. By comparison, diesel and engine oil usually release only about 3 to 4 magnesia carbon bricks per spray, and in alumina carbon bricks they may require spraying after almost every brick. This directly reduces spraying frequency, downtime, and operator workload. This page visually compares chemical anchoring with simple physical adsorption tie-in. On the Leegent 3360 side, the release film is retained more firmly on the mold surface. After multiple demolding cycles, the mold surface remains relatively clean and stable. On the conventional oil side, the film is mainly held by weak physical adsorption tie-in. It is easily carried away by the product, leaving unstable residue and requiring frequent spraying. The difference is not only visual, it directly affects release stability, production rhythm, and cleaning workload. Demolding force is one of the most important indicators for evaluating release agent performance. In the alumina carbon brick test, Leegent 3360 showed a molding force of about 5.3 kilonewtons. Diesel showed about 18.6 kilonewtons, and engine oil showed about 16.8 kilonewtons. This means Leegent 3360 reduced demolding force by more than 70% compared with diesel, and by a similar level compared with engine oil. Lower demolding force means less mechanical stress during ejection, less scratching, lower wear rate, and longer mold service life. In the reported mold life comparison, Leegent 3360 supported about 10,000 cycles, compared with about 7,500 cycles for engine oil and about 7,000 cycles for diesel. The field images make the demolding force difference easy to understand. Leegent 3360 forms a uniform and complete interfacial film, allowing the brick to separate smoothly from the mold. Diesel and engine oil show patchy residue and local sticking. This requires a much higher release force and accelerates surface damage over repeated cycles. This difference accumulates into longer mold life, lower maintenance frequency, and more stable production. High temperature stability is critical in refractory brick pressing because the mold and working environment may be hot. Conventional diesel and engine oil are prone to volatilization, carbonization, and black tar-like residue at elevated temperatures. These residues can contaminate the mold, stain the product surface, and increase sticking risk. Leegent 3360 is designed with nano-stabilization and a thermally stable film structure. According to the presented results, its volatile loss is below 3% at 150 degrees Celsius, and the residual char after high temperature pressing is below 0.01%. This helps keep both mold and product surfaces cleaner, reduces residue accumulation, and supports long duration, continuous production. The comparison on this page is very direct. After high temperature exposure, Leegent 3360 leaves the mold and product surface clean, with no obvious coke or black residue. Diesel and engine oil show significant black tar buildup and carbonized residue. This difference is important for product clean lines' mold maintenance and long-term release stability. Spray stability has a direct influence on production continuity. Leegent 3360 uses agile mechanism, nano-dispersion stabilization, and rapid volatilization. The hyper-branched polymer segments are grafted onto the nanoparticle surface, generating an electrostatic repulsion effect with a zeta potential of about -45 millivolts. This helps prevent particle aggregation and sedimentation. After spraying, the fine droplets volatilize quickly, within about 1.2 seconds, leaving almost no adhesive residue around the nozzle. In a 12-hour continuous spraying test, Leegent 3360 showed nearly 0 clogging events, while diesel showed about 23 clogging events and engine oil about 7. This means fewer interruptions, less cleaning, and more stable automatic spraying. This page shows why Leegent 3360 is less likely to block the nozzle. Its spray droplets are finer, around 35 micrometers, and they evaporate rapidly, without sticky residue. Diesel and engine oil produce coarser droplets, often above 150 micrometers, and they evaporate more slowly. This can lead to deposit buildup around the nozzle. For production, the benefit is simple: more continuous spraying and fewer shutdowns for cleaning. In real production, molds are not always new or perfectly polished. Many plants use semi-finished molds, repaired molds, or older molds with higher surface roughness. Conventional diesel and engine oil usually require a relatively smooth mold surface, typically with an RA value below 1.6 micrometers. Otherwise, poor wetting and sticking become more likely. Leegent 3360 expands the stable application range to an RA value below 6.3 micrometers. For used molds with RA around 4 to 5 micrometers, it can still provide stable demolding. Even around 7 micrometers, it may still provide emergency release capability with lower stability. This wider compatibility means higher reuse value of old molds, reduced polishing demand, and better production flexibility. Here, RA value refers to a common measure of surface roughness. It represents the average deviation of microscopic surface peaks and valleys from the mean line within a measured length. A smaller RA value means a smoother mold surface. A larger RA value means a rawer surface, which usually increases the risk of dry spots, sticking, and higher demolding resistance. Therefore, when a release agent can tolerate a wider RA range, it means stronger adaptability to rough molds, used molds, and more complex on-site conditions. This page summarizes the two most important production outcomes: demolding efficiency and mold service life. In magnesia carbon brick production, diesel released about 3.2 bricks per spray, and engine oil about 4.1 bricks per spray. Leegent 3360 released about 12 to 15 bricks per spray. In alumina carbon brick production, diesel and engine oil typically released only 1 brick per spray, while Leegent 3360 released about 4 to 5 bricks per spray. At the same time, the average usable mold life increased significantly. Diesel reached about 7,000 cycles, engine oil about 7,500 cycles, and Leegent 3360 about 10,000 cycles, representing an increase of approximately 43%. Together, higher release efficiency and longer mold life form the technical basis for lower total production cost. Cost evaluation should not only compare the Purchase price of the release agent. The right comparison is total cost per unit of finished product. Using a magnesia carbon brick plant with an annual output of 40,000 tons as an example, Leegent 3360 may not have the lowest unit purchase price, but it reduces consumption, improves release efficiency, extends mold life, and lowers scrap-related losses. In the presented cost model, the total annual direct cost per 10,000 tons is about 39,500 RMB for Leegent 3360, compared with about 53,130 RMB for diesel and about 67,290 RMB for engine oil. This represents a direct cost reduction of about 26% compared with diesel and about 41% compared with engine oil. Beyond direct cost, there are also hidden benefits: higher production capacity, lower mold maintenance cost, improved workplace safety, lower residue-related cleaning, and stronger technical competitiveness. For proper application, mold preparation is very important. Before first use, or when switching from diesel or engine oil, the mold should be cleaned thoroughly. Old oil residue, grease rust oxide scale, and loose contaminants should be removed. The surface should be dry before spraying. The recommended mold temperature before application is generally between 5 and 50 degrees Celsius. Leegent 3360 can normally be used directly without dilution. It can be applied by high pressure spray gun or manual brushing. For spraying, the recommended pressure is about 0.1 to 0.6 megapascals, with a spray distance of about 20 to 40 centimeters. The target film thickness is a thin and uniform layer, typically around 1 to 3 micrometers. Operators should avoid underspraying, excessive spraying, and local mist as the nozzle should also be checked regularly to maintain a stable spray pattern. Overall, Leegent 3360 is not only a release agent, it is an engineering solution for refractory press forming applications. Compared with conventional diesel and engine oil systems, it shows comprehensive advantages in wetting behavior, interfacial anchoring, demolding force reduction, high temperature stability, spray continuity, rough mold compatibility, and mold protection. For users, the value is practical and measurable: more stable demolding, longer mold life, lower total cost, cleaner production, safer working conditions, and higher production efficiency. The broader significance is that Leegent 3360 helps move refractory brick production away from experience-based oil release and toward a more controlled, cleaner, and more reliable engineering release system. This concludes the introduction of Leegent 3360 release agent for press-formed refractory bricks. Thank you for your attention. We welcome further technical discussion, trial evaluation, and on-site application verification.